Okay, so perhaps we can get started. Welcome everyone to the first session of this theme-based TDAI internal faculty talks for the semester. The theme that I have chosen for today's session is networks and social media. We aim to bring faculty colleagues from two different disciplines to talk about the same theme. So today we are very fortunate to have Professor Joseph Baer from the School of Communication and Professor Dena Asta from the Department of Statistics to talk to us about networks and social media. So let me start with Joseph. Professor Joseph Baer is an assistant professor in the School of Communication. Professor Baer studies the mental processes underlying social connectedness, along with their implications for individual well-being and societal change. Taking a cross-disciplinary approach, this work integrates digital traces with survey methods to understand how social cognition is changing in conjunction with communication technologies and personal networks. So over to you, Joseph.
Great, and thank you for that intro. Excited to get us kicked off here. And more generally, let me thank everyone at TDAI for the hard work and the invite here. I think we can all see all the efforts going in to bring together this really diverse community of scholars and see what we can do here and learning from one another and thinking about the contributions of theory and method together as we link things up. And so for today, my goal will be to talk about the potential of pairing mobile traces and surveys to measure social media effects. And to clarify, I'm in the School of Communication and TDAI. And we'll think a little bit about both their implications for social media effects, as well as the potential of using these kind of dual methods together more generally for testing social science theories. Now to get us going as my slides get moving here. Now my core theoretical goal here is to understand how social cognition is changing and staying the same, as the intro kind of alluded to. So in other words, I'm interested.
Sorry to interrupt. I don't think we can see your slides. At least I cannot.
Oh, I'm sorry. That must have been because we did the practice thing. Give me 1 second. Good catch. Good catch.
Yep. That's good. Thanks.
All right. Great. Yeah. So to go back to where I was going, my core theoretical goal is to understand how social cognition is changing. So in other words, what my research focuses on is how we mentally represent our social networks, our social relationships, and how we mentally process our social experiences and information in daily life, along with the role of communication technologies in modulating and moderating these processes. Of course, this global objective has become a little bit more complex as more and more technologies enter the ecosystem that we're really dealing with here. And in particular, today, I'm going to highlight the role of mobile media and start thinking about how mobile cognition more generally interacts with our technology use. So in addition to the raw number of technologies that are invading our daily lives, we are increasingly seeing how our cognition and technology is mobile itself. And so I really like this quote from a few years back from mobile technology theorist Gerard Goggin, who argues that the practices, possibilities, imaginaries, and mobilities certainly take on different forms in particular places. And I think we can generalize that to social media or communication technologies at large now with augmented and layered versions of technology use. Of course, if we kind of echo past work within the social sciences, in particular from psychology, the importance of mobile and spatial cognition is really well founded. From things like situated cognition, or how our cognition depends on the particular context that our mind is working in, to situational perception, or how we appraise different environments that we're in, to environmental psychology, like the effects of green space and blue space and being on the go and the benefits that come with them for well-being. We see how spatial context matters, and we see the value potentially of understanding the psychology of mobile technology and daily mobility together, at least in my mind, or that's what I'll argue. Same time, we are also seeing how these same technologies can be leveraged to provide insights into human cognition and emotion, and thus the potential of using mobile methods to test fundamental theories in the social sciences. And so for today, I'm going to focus on mobile traces, which we can kind of view under the broader umbrella of what are sometimes called digital traces, also known as logging, sensing, tracking methods, various terms that all get kind of at the unobtrusive nature of data collection that comes with this type of digital data. And so in recent years, we have seen how digital traces like smartphone behavior, social media logs through APIs can be used to replicate or replace or even validate self-reports and other traditional methods used in social sciences. But today I want to highlight two approaches for going one step further, in my view, which is to say potentially how we can trigger surveys using digital traces, as well as how we can annotate our digital behavior. So we can show people digital traces and have them reflect on it to get the benefits of both surveys and objectively logged data. And so here, the goal is to directly pair them, going beyond combining or linking, and think about how we can integrate lessons from survey science into digital data collection. And so today, the map for our talk is I've broken it up into two parts, essentially, which is I'll take a method forward approach, first talking about this broader project we've been working on in recent years on how we can pair mobile traces in different ways that we can answer theoretical questions doing so. And then I'm going to dig into the theme of today of social media and think about how we can measure social media in real world spaces as part of this approach. Just let me state up first, given the diverse audience of TDAI, I'm going to keep things pretty high level and go a little fast, see if we can cover a lot of ground. But feel free to reach out to me if you have any specific questions about what we're doing and what we've got planned going forward. And so to start, let's think a little bit more about how we can discuss the untapped resources of linking these different mobile methods of mobile traces and mobile surveys. And once again, kind of focusing on the way that they can be paired to understand human behavior, not just collected in parallel, especially in areas where we might think that perception or cognition is integral to the outcomes of interest that we really care about, according to our research. And so let me introduce Project MCOG, also known publicly as the Daily Mobility Study here at OSU. Project MCOG is an interdisciplinary collaboration focused on the psychological implications of both daily mobility and mobile technology, really taking this kind of rich data approach where we're diving into a smaller number of participants than what we would think of usually as big data collected from social media or smartphones, but really thinking about how we can use this rich data, sometimes called deep data or small big data, to get at a kind of a mixed understanding of both the psychological processes and the objectively logged digital behavior. In doing so, we're trying to bring together a number of disciplinary perspectives, including my home spaces of communication and psychology, and think about how we can bring these mobile traces and spatial analyses techniques to a wider landscape of social sciences, including in those fields. In doing so, we're going to take techniques from human-computer interaction and geography to understand these psychological and communication processes, as well as hopefully bring psychological and technological theories from these spaces back to these other areas in that sort of translational philosophy that we all try to abide by as part of our TDAI world here. Let me first bring up my core team here from the number of disciplines and highlight also a special thanks to my team for speeding up some analyses to make sure we had our newest data for this timely session on social media. And to give you a sense for our core sample, we collected as part of Project MCOG 450 people who completed all parts of the study, recruited from OSU's representative sample of students, as well as Facebook and Instagram ads targeted at the Columbus area. Now, participants were required to be Android users and live in Columbus, as well as volunteer to download the app that we developed to track their app use and movement. From a procedural standpoint, this was a 2-week study protocol with a baseline and endpoints kind of bookending our smartphone sensing and mobile survey period over 2 weeks. And I'm going to go through the different parts of the data set overall that we're able to bring together. And so participants were guided through an application download and tutorial. And so every 10 seconds, the study app unobtrusively collected GPS and transportation mode, according to Google, their API, as well as device information like how much the phone was it on vibration or something else, as well as whatever app was in the foreground. Now, we're not getting content. We decided to keep a little bit more privacy to not feel like people are being watched too closely, but we are getting which app people are using during this process. And so once again, we are reminded of the potential and the utility of collecting mobile traces to circumvent self-report. And you can see that here in a random sample of 100 of those 500 or so people that made up the core sample, demonstrating the wide spread of spatial context crossed by our people within the Columbus area, right? So we're really hitting all of the big blood vessels of the Columbus metropolitan area. And this sort of spatial and temporal granularity, of course, would be impossible to be captured by self-report alone. As well as getting at 10 seconds, we're really getting quite a good rate compared to the past, although that does depend a little bit on some automated battery collection issues and things related to how Android operates. But moving beyond just getting data that we would have trouble getting without self-report, I also want to think a little bit about linking them. How can we connect both to blend the benefits of both perceptual and objectively logged data? And so building on this deep foundation of ESM and EMA research related to event contingent responses, and adding a digital twist, that you might think of it as, which is to say, how can we trigger surveys via mobile traces to target theoretically relevant spatial context? So for instance, say we want to test the relationship between time perception and being on the go, kind of building on this link between spatial and temporal perception that's been theorized. Now, measuring when people are on the go and getting those cognitive or perceptual measures is difficult. But if we're tracking people, and then when we, as soon as people start to walk, we send them a mobile survey at that moment, all of a sudden we're able to capture some hard to measure context and get at that kind of mixed advantages of surveys and log data. And so overall, we got 29,000 or so triggered or random surveys taking this kind of approach. And so it was a mixed approach. So they would get 1 or 2 minute surveys and get 6 per day, no matter whether or not they got triggered walking ones for each one. So they didn't really know where the survey came from, what was the source of the trigger, giving us some greater naturalistic or ecological validity, while still allowing us to target that theoretical context of being on the go. And then taking another step beyond traditional experience sampling method, we can ask participants to reflect on their behavior by showing them their own digital traces side by side with the survey. And so, for example, another sub-study within this project that we're finishing up, we were interested in whether mHealth apps actually make people more active. And so being able to draw on both subjective and objective data related to mobility is really helpful for us to be able to delineate this kind of perception versus behavior gap question. And the short answer, in case you're wondering, is that they don't. It seems like people think that mHealth apps make them more active, but in reality, the people who used mHealth apps more were not physically more active, according to our data. And so just give you a little bit better sense for how this operates. Here we're providing cues and context by showing people the actual trips that they did in their daily life, and they would have 24 hours to sort of answer these trip-based surveys, building on some recent kind of work over the last couple of years in transportation and geography, and thinking more generally about how we can get that psychological mentality toward how people understand spaces and movement in daily life. And so our goal here is to improve the self-report accuracy and completeness by connecting those two sources, but in addition, to be able to have directly linked, objectively logged trips, as well as how people construe or appraise those trips psychologically at the same time. And we were able to get 48,000 of those or so from that sample. So altogether, we get a fairly deep data set, that rich data set of about 75,000 mobile surveys in conjunction with 30 million or so smartphone logs, all within this kind of 450 core sample. And so once again, the advantage here in prioritizing ecological validity and real world perception as opposed to just getting a lot of people. And so our goal more broadly is to sort of advance this open team and slow science approach to the psychology of spatial mobility and think about how we can kind of link these interests related to mobility across disciplines, echoing the translational aims of TDAI. As a couple of things we have coming up, we're going to be also releasing a tutorial for using GPS in psychological and communication research, as well as trying to provide simulated urban mobility data based on this deep data set that we've been able to generate. And finally, having best practices for paired mobile designs for social scientists across different disciplines. And so now to dive quickly and pivot with enough time, hopefully, toward our social media focus for today. I want to think a little bit about how we can adopt these approaches to measure social media and try to deal with some of the conflicting and contradictory findings that we see both in society and in the research literature related to social media. And so in particular, I'm going to make the case for testing the interaction of technology and spatial behavior and how they might matter jointly. And of course, as captured powerfully recently in the cultural object that is now the social dilemma, as many of you may have seen. And I'm going to just sidebar, I'm going to ignore the political challenges that are clearly putting us down an uncertain path that we don't want to go. But for now, focusing on the psychology of social media and what those implications might be. And I would be a bad communication researcher if I didn't mention the historical mindset that is important to keep in mind, which is that one of the core perspectives from our field is that whenever these new technologies or media enter society, they are generally going to generate a lot of alarm, particularly in relation to potential psychological fabric that might, so for example, classically, the example of the telephone coming to the home, there was lots of concern that that would disrupt how families operate. We were able to survive, but of course there are also psychological challenges that come with these cultural changes. So trying to put that kind of narrative in context, which is why there's been a lot of research more recently in trying to put together the story, given the thousands of studies that have been published now on the relationship between social media and mental well-being. And so I'm going to really focus here on the mental well-being, or what we might call emotional well-being implications of social media. And so more recently, the more representative, longitudinal, and meta-analytic studies that we've seen come out have kind of questioned this idea that there is a strong effect of social media on individuals, especially when you kind of adopt more stringent sensitivity analyses and statistical approaches, and really highlighting the importance of data science for how we make sense of these cultural objects in society. Now, more recently, we just completed a review where we tried to pull together some of these different narratives on the implications of social media, and came away with kind of 3 or 4, I'm going to highlight 3 key points, which are: 1, that social media do increase social resources in general, but they also come with a different set of social stressors, as we all know. Potentially increasing, especially when we're looking at passive use of feeds or streams, when like we see posts on Twitter or Facebook, the role of social comparison and how we kind of can elevate it through these social contexts online, and the challenge of envy that can lead to negative well-being in some cases, as well as the kind of extra connectedness and distraction that we all know too well. But beyond these kind of general narratives, if we tried to aggregate what is the positive or negative effect of social media on emotional well-being, we come away with this mixed story that it really depends. It depends on a lot of different factors, ranging from the personality and goals of people, to the practices and the technical affordances of the technologies, to the platforms and ecosystems that make these technologies and who we're interacting with. And so what I'm going to do is argue that one way that we can kind of try to move forward in a more contextual view is, and make sense of these kind of different factors and processes that are all happening in conjunction with one another, given the complexity of human behavior, is that we can take spatial context and other situational contexts as a way of anchoring our understanding more clearly. And so I'm going to use spatial context to refer to on-the-go or transit states, as well as kind of key locations, in particular today, home or work. And this builds on some past work that we've done where we tested the potential role of self-reported spatial context on social media using another triggering approach to mobile traces, in which we tracked individuals' use of Facebook via the Facebook API. And then whenever somebody posted on Facebook, we would send them a mobile survey in the 5 minutes following it. So once again, get that blended benefits. And so by tracking their posting and commenting behavior via this, we were able to get this more granular and contextual understanding of how Facebook might affect emotional well-being in daily life. And perhaps the most noteworthy finding for us that came out of that was the idea that Facebook posting increased emotional arousal, but only when participants reported being home. And so we do see this kind of moderation effect of spatial context in terms of how our emotions might fluctuate as a function of our technology use. Leading to this more broad question that I'll kind of tackle and bring up today, which is: how does social media affect our mood in real world spatial context, where we draw on all of the methods that have been used in other fields to get this kind of deeper understanding of space. And so once again, diving back into this broader project that we've been working on, we can kind of zone in on the social media apps that we kind of reported, which not surprisingly made up a good share of that overall 30 million points. So we see about 3.5 million social media logs logged every 10 seconds that we captured. In addition, we have those mobile surveys that we were triggering throughout daily life, and we captured emotional valence and arousal, typically considered the two most fundamental dimensions of emotion and mood. And in doing so, we're able to capitalize on that triggered survey approach once again, right, by looking at how social media might matter differently when individuals are on the go versus in static locations. We're also able to once again use the mixed objective and subjective approach to cross-validate the messy data that you get from apps on Android by asking individuals to reflect on their app use afterward, and then hand coding their top 8 apps to ensure that we are capturing the apps that we think we are. And so once again, this allowed us to leverage the ecological validity of our approach. And so I'm just going to present some initial linear mixed effects models where we account for the nested nature of the data. And really here we're interested right in the role of social media use predicting emotional well-being. And we looked at this at 10-minute, 30-minute, and 60-minute intervals. So how much did people use their social media apps in the 10 minutes, 30 minutes, and 60 minutes prior to when we collected that mood response. And we're controlling here for a number of temporal context variables, as well as just sort of general demographic variables. And so what we find in our first set of analyses is that there is really no effect. So kind of echoing this minimal effects hypothesis that has been kind of drawn out through more kind of stringent statistical analyses, we are seeing kind of very minimal effects in terms of how much people are using social media objectively and whether that's having a relationship with their emotion in daily life. Now, we also want to ensure that these kind of effects do not depend on spatial context and start thinking about that interaction. And this is particularly important when we think about how different our mobility behaviors can be, right? So as we saw within that map of 100 people, here I'm showing you 2 different people. And in one case, we have somebody who's kind of localized around the city center, and they're in a smaller number of key locations in their daily life over the 2 weeks, or somebody else who's driving throughout a much wider array of contexts and situations. And so thinking about how social media may mean different things, once again, different possibilities as a function of where you are in daily life is something that I think we have to account for. And so once again, we've got those, both the experience sampling service as well as the logged data and transportation mode from Google. And here we're going to look at those 2 different forms of spatial context and the interaction really between social media use and location on mood. And further echoing this minimal effects hypothesis, we do not see any interaction, at least in terms of our log data, the objectively logged data between social media use and location on either emotional valence, or how positive or negative individuals feel, or how emotionally aroused they feel. So overall, no meaningful effects observed on daily mood. At the same time, what we are also starting to see is that these types of effects depend on more person-specific approaches to analysis. And so they reinforce calls to think about how, for instance, in this recently published study, how there was about a positive relationship found for about 45% of people, but only a negative relationship for 8% of people. And this suggests that while there might be kind of aggregate null effects, there could be important effects for certain personalities or subsets of individuals. And so our next step in these analyses that we're just pushing forward now with recent data is to think about how person and space-based and analytic approaches might matter together, taking a more dynamic approach to modeling, as well as starting to really draw on that perceptual data of space, right? So thus far, we've just looked at whether there's an interaction between objectively logged space and social media use. But if we really think that these are perceptual outcomes, mood, and how we understand these psychological implications, then it might be more important to really think about how individuals kind of understand and make sense of their daily mobility in combination with these technology effects. And we might see a different story. Bringing me back to sort of our overall sort of map for today, which is the value potentially of pairing mobile traces and surveys, as well as doing so in the context of social media to try to clarify these this unclear literature on how these technologies are impacting our mental health. And more generally, thinking about how we can measure cognitive and perceptual processes in a more dynamic way that accounts for space to get at this complex story of how we think throughout daily life. And so I have some other theoretical work thinking about how our technologies are shaping our social networks, our mental social networks, and who comes to mind in daily life, and how we've started to see how these different mental processes and networks that emerge can have different implications for our emotional and social resources, and thus bolstering the importance of statistical methods for measuring dynamic social networks, which is why I'm excited to hear from Dena next on some of the things she's working on to kind of capture and measure and statistically analyze more dynamic approaches to networks. So thank you for your time. Hope you had a good time.
Thanks a lot, Joseph, for the great talk. If there are any questions for Joseph, please write them in the chat or just raise your hand and we can unmute you. Questions or comments or any discussion you want to do? Oh, I see Tanya. All right, Tanya, you're in.
Yeah, so great talk, Joe, and it's really, really nice way of kind of seeing the overall our kind of effects of different themes. So one of the sort of the tensions that we see in this kind of research that is both online, offline, and how to is particularly right now, particularly acute in measuring pandemic activity and impact.
Yeah.
And the interplays of what we need to know, what we would like to know versus right. The do no harm in the process. And the aspects of self-selection of people Absolutely. Who go into this. Mm-hmm. So my question is less of a specific question, but if you like a prompt for your thoughts and comments in that direction.
I'll tell you, I think, as somebody who tries to measure or at least provide insights into how technologies are affecting whatever social or cognitive process or outcome you're talking about, it is just very hard to capture these kind of historical cultural changes over time because of how things are so interlocked. And selection is a big part. Now, I think part of it is you need more representative samples, but of course, given, in a lot of these cases, for example, you don't want to force people to give you their digital data. And so we do rely on some ways even more volunteer-based approaches to getting at some of these digital data sets, which I think exaggerates some of the generalizability issues for sure. I think that's a separate question from the theoretical challenge of measuring how things that are interwoven, what is the true effect, for instance, of social media when everything is so embedded in daily life. And so all the effects are kind of bidirectional, almost by definition. Is that sort of getting at, other than essentially acknowledging that those are issues, I'm not sure I'm totally giving you a solution, but.
No, this is great. And I mean, it's clearly a bigger conversation. And so maybe related, a follow-up question to this, also from watching pandemic and being involved in data analytics aspects of it, there is the expectation that that we can get answers by looking at digital traces online or Wi-Fi or whatever and sort of from the work that you've presented, good answers take time, and
yes,
and particularly this digital mess is not necessarily the answer to the quick. It's more the answer to the dirty.
Yeah.
And right. So I really like that you're really comparing the kind of old school surveys to digital and really telling us of how much power the new ways of answering these questions take. So, but back to like, how much can we expect from this mode of?
Yeah, in terms of actually being able to kind of delineate what the true effect of technology is, you mean, or just generally thinking about the limitations of digital traces?
More generally, yeah, your comments on limitations of digital traces and
personally, I mean, in some ways, it's because of the limitations that I've found when trying to answer my more theoretical agenda that I've kind of pushed back into the value of surveys and thinking about ways to link them, because I've just, for instance, when I was doing my dissertation, and using the Facebook API based personal networks, and then, they take away the API. And then also while I'm doing analytics, and generating those measures, the actual Facebook posts we're using to generate the networks are changing over time. I think it definitely made me think of digital traces more as, it's a tool for getting at, on their own, I still need more data to answer the questions that we're trying to get at. And I mean, you have work, of course, on, thinking about dynamic networks. And so when I think this is one of the challenges is like, when if we just rely on one data set, we're obviously not going to understand somebody's overall social network today. The ecosystem is too complex. Our networks are highly layered. And so while we can learn network dynamics within a given trace data set, to understand that kind of broader question that I'm more theoretically driven by of how are the technologies changing, who are the people that we interact with, and how are we thinking about the world? That's where we need to use a mixture of, in my mind, the self-report and those digital traces, because the digital traces are changing too much. And there's a recent David Laser piece I think they put out, is like a follow-up in some ways to the In Science, on the challenges of this, and in part because a lot of the early stuff was really relying on the kind of corporate data that's even harder to come by now. And so how do we approach this problem where we can maybe contribute digital data sets more, there needs to be ethically produced large scale digital data collections that are standardized over time, as opposed to kind of this haphazard fine data set where you get, even though we learn a lot, of course, from those approaches too. At least that's my sense.
Yeah, I have a very follow-up related question. So is it possible to estimate some sort of network effect of the social media effect from your data set? So you can think about that, whose content they're viewing, not just what type of content they're viewing.
So using the app as like network, as part of the network. Yeah, that's interesting. I've seen there's a project that's coming out, Stanford. There's a big group of people at Stanford that are doing something called the Screenomics Project, which I just presented earlier this week with them too. And they're really thinking about how to pull more of a network approach into analyzing, the kind of the really nonlinear dynamics of how we go between apps. And it wasn't, I was watching their presentation. I was like, oh yeah, this might be the way to do it, because it really is. I mean, our data is not as deep as theirs, although it's still, I mean, if you're getting 10 seconds, we have a lot of apps. And so thinking more generally about what leads to what, and especially if you do have deeper content measures, I think there is definitely a lot of potential there. I haven't done that type of network analysis before, but that's where, I'm excited that there's a lot of people around who might jump on that.
Okay, I think we have time for one last question, and there is one in the Q&A chat, so I'm just going to read it out. You mentioned, so this is from Emma Wenschkowski, sorry if I'm pronouncing it wrong. You mentioned that there is greater emotional arousal when posting on social media at home, where people posting more at home or on the go. With everyone at home now, how do you think social media's effect on people's emotions has changed in the middle of the pandemic?
This is a good question. Yeah, and this is the interesting. On one hand, I'm kind of, it's funny. Our data collection ended for the OSU daily mobility study in December of 2019, and so depending on your perspective, it's at least it's not kind of confounded with the pandemic world. But on the other hand, I think there are some important changes and we are learning a lot of things from that kind of contrast effect, as I think Tanya alluded to. And so in terms of the core question of how much are people posting at home, this is something that we're planning to kind of dig a little bit deeper into how much. I mean, people spend a lot of time at home. And so even before the pandemic, which is our data set, a large share of their social media activity is at home. Now, to the question of how it's changed with the pandemic, I think, in some ways, the way I think about it psychologically is how have we recalibrated how we use, like, where we're doing different things and where our emotions are. There's a theory we're drawing on to test some of these ideas, which is called optimal stimulation level theory, which is that the idea that we're all trying to maintain this optimal level of arousal and stimulation. And so part of what we want to test is whether we're moving between spaces and using particular spaces like the relaxed, restorative environment of home to maintain that equilibrium. And so I don't have the answers yet, but I think those are good questions.
Great, thank you. So there will be more opportunity to ask questions, Joseph, at the end of Dena's talk. So let's move on to our next speaker now. And thank you, Joseph, for this excellent talk.
Great, thanks for having me.
So next speaker is Professor Dena Asta. Professor Dena Asta is an assistant professor in the Department of Statistics. Professor Asta's research interests include network inference and non-parametric methods on non-Euclidean spaces. Network inference aims to give statistically rigorous methods for analyzing and comparing brain networks, collaboration networks, and other real-world networks, while non-parametric methods on non-Euclidean spaces adopt non-parametric methods of inference to data that naturally lives in spaces other than Euclidean space. Such data, for example, arises in brain imaging, astrostatistics, and radar tracking. So Dena, over to you now.
Thanks, Subhadeep. And thanks, TDA, for the invitation to come give a talk. And that was really interesting, Joseph, your talk. So thank you for that as well. Let me go ahead and start sharing the screen here. Okay. All right. So my talk is regarding, and just to note, the title of the talk was incorrect on the advertisement for the talk, so I might be throwing you a bit of a loop, but my talk is in fact about statistical networks with underlining geometry. And this type of talk is going to comprise some collaborative work with multiple individuals. Kate Calder, who's now at University of Texas, Austin, my thesis advisor, Cosma Shalizi, who's at Carnegie Mellon, as well as Anna Smith, who's at University of Kentucky. Okay, so it kind of will be a couple of bits of research compiled with those individuals. The overall idea of my talk is really about how do you actually utilize the underlying geometry of networks to come up with more efficient, statistically rigorous tools in analyzing networks. So that's the general idea. Now I'm going to kind of just give more of an overview of this research, given the fact that we have such a diverse body at TDAI. And if interested in more details of it, be happy to answer any of those questions if any arise. Okay. All right, so to start out, before we can even talk about the type of statistical tools in analyzing networks, we should really first talk about the type of generative model that I'm actually using in talking about coming up with more rigorous tools in analyzing networks. So in order to motivate the type of generative model that I use, I'm going to just talk about some ideal aspects of a generative model that you would want. First is that you would ideally want a generative model that is independent of size and label of the network. Okay, so that way when you're doing inference, it ignores the sizes and labels. That way you can compare two networks of different labels or compare two networks of different sizes to really understand if they're coming from the same underlying distribution. Okay, so essentially you want a generative model that ignores those types of features of a network. Second ideal aspect of a generative model is the fact that it actually generates networks that you see in the real world. Okay, since those are essentially the ones that you actually want to analyze, we want to be able to have that generative network model that can generate those types of networks. And lastly, we want it to be able to preserve the geometric features, since my statistical tools are really using that underlying geometric features of those networks. So I want a generative model that preserves those geometric features. And a natural choice.
I'm sorry, can I quickly interrupt? Because
Sure.
I just want to clarify before we get too deeply into this. Dena, when you talk about generative models, are you talking about algorithmic or statistical generative model? So maybe define the term generative model for the broader audience.
Yeah, a statistical way of generating networks from a particular distribution.
So a model means that some broad parameters of the resulting network are statistically equivalent to real ones, or just to, because I'm sure that there is the notion of generative models across different disciplines.
Right, yeah. So let me maybe actually go into the actual generative model here to kind of explain it a little bit more. Generative model, continuous latent space model, which is essentially where you're defining a distribution on some continuous space, and you're sampling a bunch of points from that particular distribution. And essentially the way the network gets generated is where you are attaching edges between those points with probability, with higher probability when those points are closer to one another in that latent space, and with a lower probability when those points are further away from one another. So that's essentially what I can mean in terms of the generative model and the ideal generative model specifically that I would like to use here. Tanya, did that address your question?
Yes, thank you. So we're not expecting like, oh, this is like how actual real network looks, but it looks overall like real networks look.
Right. So the idea is that you want a generative model that does generate networks that have characteristics that you see in the real world networks. Right. And I'll go in more in detail about that a little bit later on. Okay. All right. So ideally, to have these features, these ideal features of a generative model, what arises is something called a continuous latent space model, as described there, where you're kind of sampling points from some underlying distribution and connecting edges with probability increasing, decreasing based on the distance between those points on the latent space. And essentially, you can really think of this model as just describing the network as a density on this space. So that way, it gives you a more elegant way of thinking about networks. You're thinking of large networks as just approximations of geometric objects. And this gives us a more tractable and elegant way of describing networks versus the messy combinatorial ways, such as adjacency matrices of describing the network here. Here we can think of networks being described as just a density on a smooth space. Okay, so we're dealing with densities versus these messy combinatorial matrices. And this is nice because then it allows us to use a lot more tools, for example, from analysis and differential geometry. And in essence, it also allows us to do things more elegantly, such as if you're comparing two networks, you can think of taking the L2 differences of those densities characterizing those networks. Okay. Okay, so to kind of go into a little bit more detail of what type of geometric space that continuous latent space model should be defined on, I'm just going to go over some work that I did with Kate Calder and Anna Smith, in where we kind of explore that question, the relationship between the geometry of the latent space and the combinatorial features of the networks that we've observed as well as generated. And what I do in order to be able to talk about that is I look at something called a graph Laplacian, the eigenvalues of a graph Laplacian, which kind of describes the geometry of a network. Okay, so I won't go into detail what that specifically is, but essentially I'm looking at the characteristics of that network in terms of the eigenvalues of the graph Laplacian. And as I'm kind of mapping that out here in these graphs, where the purple line here is really representing those characteristics that coming from the actual real world networks here that I have on the left side. And on the right side are those graphs that are kind of graphing those characteristics alongside with networks generated from three types of geometric space models. One of positively spaced, which is green, one of flat curvature, which is blue, and then one of negatively curved, which is red. Okay, and I'll talk more about what those geometries really are describing here. But essentially, looking at a bunch of real world networks that are usually popular for people in network research area, they've looked at, for example, the first network here is called the Zachary Karate's Club, and this is essentially recording the social interactions of 35 members of a karate club back in the 1970s. And essentially, when you look at those geometric features of the networks described by the eigenvalues of the graph Laplacian, they align with the negatively curved generated networks here in the red line. Other examples of even higher nodes, for example, the Chicago Transportation Network, just to kind of give you another variety here, another network in the real world. This is a road transportation network made of 1,400 nodes representing traffic zones and ties representing those leaks by freeways and other roads. And similarly, you can see it's going to be more along of a negatively curved related geometric space versus a positively or flat curved. Okay, so there's a variety of other networks here of different sizes and intricacies here and how they're interconnected. And you can see that most of the ones that we've observed in the real world here are just a variety of them, mostly lined up with the negatively curved geometric space here. Okay. Okay. So let me just kind of step back a little bit, and if you're, for the individuals in this audience that are not quite sure, when I say negatively curved space, positively curved space, and flat curved space, what do I mean by that? Essentially, positively curved space, an example would that be like a sphere, and the way you kind of differentiate between these geometric spaces is if you put 3 points on each of these spaces and connect edges between those 3 points, and you're adding up the angles within that triangle, you would get an angle that is greater than 180 for positively curved space, less than 180 for a negatively curved space, and exactly 180 for a flat curved space. So that's kind of the way of describing the different geometry of these spaces here. And I highlight the negatively curved space since we're showing that that tends to line up with some of the geometric features that we see in real world networks. Okay. So ideally, when we talk about a generative model, the continuous latent space model, defining that density on some particular latent space, we're talking about defining it on a negatively curved space. Okay, and then generating it by sampling points from that particular density, and again, attaching edges with probability, increasing, decreasing based on the distances between those points. Okay. Now, giving you some general intuition of why we actually would want to choose a negatively curved space is essentially that that negatively curved space is representative of real world networks because they tend to be hierarchical and tree-like in structure. And in fact, those hierarchical tree-like structures can even be thought of as a negatively curved metric space, where the metric on there is really referring to the shortest path length. Another kind of intuition of why negatively curved space makes sense is real world networks, again, have these tree-like features. There are certain space limitations that are going to occur with positively and flat curved spaces. For example, if you put a ball inside one of those spaces and you grow it out with respect to its radius, in a positively curved space and a flat curved space is going to grow polynomially, and it's going to have spatial limitations for something that has a tree-like structure that grows exponentially. However, if you grow that ball out with respect to its radius in that negatively curved space, it will also kind of grow exponentially. So there's certain space limitations with those other types of curved spaces that negatively curved space accommodates what we see in the real world. And also another kind of just like a general understanding of why that space makes sense is typically when you think about a very large social network and you're looking at 2 peripheral users on that very large social network, and you ultimately want to map out the shortest path length between those 2 peripheral users, you're most likely going to have to go through some super user in the center. Okay, that's very interconnected. Well, similarly, kind of a slight simplification of a negatively curved space is you can think of a cereal bowl. On a cereal bowl, if you think about 2 points on the rim of it, that shortest path between those 2 points on the serial Bose rim may end up being going through down to the center and then back up to that other point on the rim. So intuitively, that geometry that you see in real world networks is really mimicking the geometry of what you see in negatively curved space. Okay, so kind of like a serial Bose is kind of a very simplification. It's obviously not completely accurate, but a very like crude simplification of what a hyperboloid or negatively curved space represents. Okay. Okay, so negatively curved space, what type? It's called H2, a two-dimensional hyperbolic space. What I've done here is just kind of shown you some isometric representations of H2. The very first one is just the hyperboloid, again, kind of the crude representation of a serial Bose, not completely accurate, but kind of gives you the general idea. Another representation is the Poincare disk. If any of you guys are fans of MC Escher, he plays around a lot with the Poincare disk and displaying some of his art. So if you're familiar with it, you will understand what I mean. And in the Poincare disk here, the shortest paths are really being represented by those dark curved lines. So they're not straight lines, they're actually curved lines. Another isometric representation, equivalent representation, is the Poincare half plane here on the very right. Okay, so just to kind of give you a general idea of what that space represents. Okay. Okay, so there's been some work done by Kryukov and others, and where they've used they've defined a parametric model where if you draw points from that particular model, as I tried to display here, the green dots are points sampled from some parametric uniform density on H2. What ends up happening is once you've generated the graph on the right side by essentially attaching edges between those points with probability higher when the points are closer to one another and further away, less likely, the kind of graphs that you're generating are the ones that you're going to see in the real world network, in the sense that they have the characteristics of what you would see in a real world network: clusterability, highly skewed degree distributions, and so on. Okay. So my extension of that is to not just think about networks generated from necessarily a quasi-uniform defined distribution on H2, but draw nodes from arbitrary densities on H2 in order to come up with a non-parametric model in generating networks. So let me kind of quickly go here. So the idea is that if you fix some node density, you fix that distribution over graphs, you are able to generate networks that have similar features with one another. And the idea that what we essentially want to do is be able to go backwards, where if you fix the distribution graphs, the same distribution, can you be able to basically infer that from just observing an actual network? Okay. So here's just kind of the general methodology here. The idea is that you've observed some network in order to preserve those geometric features, that information that kind of helps us characterize that network. You're going to embed it into this negatively curved space here. And then from that, once you've embedded those points such that the distances between those points are really reflecting the interconnection between those nodes, you do some kind of density estimates of those points. And then you have some inferred node density that essentially, if you generate a graph from that node density, you would get graphs similar to the ones that you actually start out with. So that's kind of the general methodology network inference. And I'm just going to kind of go quickly over each of those parts just to kind of give you an idea of how that actually gets implemented. First part, how do you actually do that embedding? Well, we end up in practice using a multidimensional scaling method. So that algorithm is essentially exploiting the geometry of the networks in order to do that. And then in practice, to kind of show you how it is, the very bottom right corner is where we sample a bunch of points from some particular density on H2. And then that is basically essentially generating the network on the very top left corner here. And if you try to use the generalized MDS, it looks like the center graph, which kind of shows a similar pattern and shape as the one that we started out with. Okay, so that's how it does it in practice. One note to make about that is that the consistency result that have worked on for this particular type of estimator, we were not able to do it for a multiple dimensional scaling embedding method. We're only able to prove it for a maximum likelihood estimate. So obviously there's some challenges with that, because MLE obviously are harder to calculate than an MDS. So just kind of to note that. Okay, now what happens once you've embedded that network? Essentially, you want to estimate the density of it. So we do so with a tool that I worked on that it kind of generalizes as something called a kernel density estimator for these other types of spaces, like a two-dimensional hyperbolic space, in order to get a node density of those sample points. Okay, so that's essentially how it's done. We have some observed network that we're interested in analyzing. We've embedded in some continuous latent space model respecting those geometric features, and then infer some node density that essentially, if you generate another network from, you are observing networks with similar features as the ones that you can generate from that inferred node density. Okay, so why is this, how does this help us with terms of application? Well, there's multiple different applications that can arise now that you have a kind of a consistent network estimator. When it comes in terms of network resampling, you can think about doing unique prediction, data recovery, or simulation, modeling, bootstrapping, and so on, as well as network comparison, which I'll kind of focus on a little bit. Why network comparison is useful is when you want to do things like disease detection or medical diagnoses, or any other kind of large-scale data analysis. Okay, so I'll focus on one of these applications, network comparison here, and give just a couple of examples of where it arises. For example, gene regulatory networks. In order to do network comparison to determine if there's differences in the phenotypes from differences in those networks. Other examples are brain networks, where the nodes are the anatomical regions of the brain, and edges are large enough correlations between those activity, for example, the blood flow, to be able to do things such as diagnose patients with certain illnesses, or being able to predict behavior from that brain activity. Okay, so there's plenty of applications where network comparison, coming up with a statistically rigorous way of doing it, can be useful. So you may ask, well, what exactly has been done? And typically what usually is done in those cases are where people are comparing summary statistics, for example, average path lengths or triangle densities or clustering coefficients. And what happens is when you use these type of summary statistics, it kind of misses out on the overall geometric features of these networks. And you're not even able to distinguish between a grid-like network versus a tree-like structure network. So there are some problems when we use those type of summary statistics that kind of require some more statistically rigorous tools. So what is the framework in doing network comparison in the context of how I've defined the network estimator? How do we actually go about doing that? Essentially, the idea is that if you start out with two networks here that you've observed, N1 and N2, the idea is you use that network estimator to infer those node densities. And essentially what you want to test is to see if the difference between those two are statistically significant up to an isometry. And again, I've been saying isometry a lot. For some of you who are not familiar, what I mean by that is just like translations, rotations on Euclidean space. Okay. So in essence, to do that, to determine if it's statistically significant, we need to estimate the distribution of the test statistic under the null hypothesis. So how is this done? Well, it's a general method of bootstrapping to get that null hypothesis distribution of the test statistics is where you are starting out with your two observed networks and inferring a joint density, and then repeating the last two steps over and over and over, where you are essentially generating two new networks and then inferring those two node densities and doing that over and over again to define that distribution of the null hypothesis. Okay, so that kind of gives you just a kind of a quick overall summary of my research. Okay, I'm not sure if I ran out of complete time, Subhadeep, so I'll go ahead and end there and see if anyone has any questions.
Fine. We have time left.
Okay.
So, okay, so do you want to stop here, Dena?
Yeah, I'll stop
Oh,
here.
okay, great. Well, thank you. This was a very exciting talk. Are there any questions that we can take? Tanya had a question that she has posted in the Q&A, so I'm going to read that up. Deep graph
or I
network.
can ask
sure,
because I also
sure.
unfortunately I have to run off in 2 minutes.
Please go ahead.
Sorry, but really interesting, and this is really close, very close to my heart. So I'd love to follow up in general more closely, Dena. But a general question is, well, somewhat general for some audience, general, is that in recent machine learning approaches, particularly deep learning approaches, also there's a whole line of graph learning, right, where you which take the entire network and embed it in some latent space, and there is a line of it where you do like node embeddings, right? So node kernels, and then embed the structure of the network down to each node in some latent space. These latent spaces now also increasingly used for building machine learning, which is why I wanted to make a distinction from the beginning. Machine learning generative models, which generate networks that look like whatever that learned networks are from that latent space. So has anybody looked at the properties of that latent embedding space? Does it have any connection to the properties of these spaces where you intentionally choose an embedding space? If so, are there any similarities for specifically maybe geometric networks?
Okay, so I can't speak specifically on the machine learning literature. I have seen it, but I haven't like gone very in depth in it. If I think I understand your question, you're asking what are the kind of features you see in these continuous latent spaces and how do they line up with the geometric features of the networks that we're observing? Is that kind of generally?
No, maybe we should take it offline because I do.
Okay.
Yeah, but my question was about the features of the latent spaces that are resulting from machine learning embeddings versus the latent spaces or embedding spaces that you're using here. So do they compare in any way? But I think we'll have to take that discussion offline.
Okay. All right.
Yeah.
Fair enough.
Sorry. Thank you.
Okay. Any other questions?
I have a question if we have one.
Oh yeah, sure, absolutely.
So how does this interact with temporal networks? Like, so you're talking about network comparisons, and we can think about it as like two different networks, or we can think about one network over time. Is that something that's built into your thinking, or how does that affect the process?
Yeah, no, temporal networks, that's actually something we haven't explored with regards to this kind of framework. I know Subhadeep is thinking about that. So we have many discussions together on that. And I know he's working more in that area. So I'm just like thinking about one time of the network. And in essence, that way of kind of defining consistency and everything like that is uniquely defined as the network, not the number of observations of those networks growing, but the number of nodes of that network growing, kind of in that essence.
Fluctuations in the overall network structure over time.
Yeah. Mm-hmm. Yeah.
Cool. Yeah. No, I'm curious. I mean, I think that's where I think I also see connections to some of the, because we've done we have worked on more of the fMRI data where we've used some simple network models on that type of data, and it is both within person and we want across person, but we also want that within person comparisons over time. And I always wonder about it because I'm always thinking, yeah, we're confounding different network features, so it's cool to see how you're starting to think about that in your work.
Yeah. Yeah, no, that's a further discussion with Subhadeep down the road.
Yeah. One thing at a time. Get through the pandemic.
Right. Other questions? I have asked Dena too many questions over the last few years, so so just give a chance to anybody else if there is any question or discussion. Okay, perhaps now, yeah, perhaps then maybe we can end the webinar for this. Dev, do you want to say something before we end?
Thank you so much for doing these talks today. It's been amazing to hear from you, and thanks to our audience for being here and for asking such great questions. And we'll see you the next time.
Okay. All right, thank
Have
you,
a great day,
everyone.
everybody.
All right,
Bye.
thank you. Bye-bye.
Bye.
Everyone.